Okay, so last class we did this activity. This is the last thing we did, right? We converted 12 grams to milligram and then 12 grams to ounces. And we said we read this question and we said hold on to that. We will answer this later. That is why our answer is not given as 0.42 or 0.4234 or whatever you saw on your calculator screen, because we have to express our answers according to the significant figures rule, which we will learn in a couple of slides. So what are significant figures? That is the question we have right now. Before we go there, we will look into a couple of more basic units. Another unit we would work with very often is volume. And volume is defined as the amount of space occupied by a substance. Whatever space a substance needs to exist, that total space is called volume. So when we say space, it is three-dimensional now. It has length, width, and height. So when you have these three physical quantities, and if you want to calculate the volume, all you have to do is multiply those three quantities. Volume is length times width times height, or V is LWH. That is one of the easy formulas to remember. And the common units we use for volume in science calculations are centimeter cubed or milliliters. Okay, so here is a picture of the right side picture is three different types of bottles which we would use in our day-to-day life: juice, water bottles, and the volume will be written on the bottle, right? Now when the bottles are of different shape, they would come in, as you can see, towards the cap they are kind of narrow, and the bottom, some of them have different shapes, twisted, funky, all that shapes. So when something is like that, it's not easy to calculate the volume from the bottle, right? Because the width or height or length, they may not be exactly the same. So in such cases, what do? We can pour the substance in the bottle to a container which is actually calibrated and marked for its volume, and we can measure the volume. So on the left side you would see different containers we would use in lab to measure the volume. The one in the middle, that long glass tube with numbers written on it, lines and numbers, that is called a graduated cylinder. You will be using that very often in the lab to measure some volumes. There are different graduated cylinders. This one is a 1 liter graduated cylinder, but there are smaller ones for smaller amounts and larger ones for when you are working with larger amounts. And then the other two glassware which is given, they are called volumetric flask, and they do not have lines like in a graduated cylinder. Volumetric flasks are made for like one flask is made for only one particular number. Say for example the left one, it looks like it is a 250 ml volumetric flask. So the only line you will see is on that narrow neck, there is just one line. So when you fill something up to that line, it's exactly 250 ml. You cannot go above the line or below the line because you don't know above or below what it is. So that is very specifically made for one particular measurement only. So you have different sizes of volumetric flasks also. Now, as I said, the common units for volume we will use is centimeter cubed and milliliter. Please keep in mind this important relationship. That is, shouldn't I take the pens before to do it again? That is 1 centimeter cubed is exactly the same as 1 milliliter. Okay, both of these units are used in chemistry and in physics and other calculations. Sometimes the problem would give you a milliliter quantity And when you work with, the problem, when you do further steps, you may have to convert that to centimeters. So remember this relationship. It will not be given in the problem, but you need to be aware of this. 1 centimeter cubed is exactly the same as 1 milliliter. Yes?
Are we going to be expected to memorize like the Kelvin, all those?
No, but you need to know the basic units. Like we will be coming to the temperature, and then I would tell you that, okay? So once again, volume, as I said, it's length multiplied by width multiplied by height. So if you have a geometric figure which has a specific length, width and height, all you have to do is multiply those three quantities and you have the volume of the geometric figure. Here is one of the very familiar geometric figures, a cube. When we say a cube, what sort of a geometric figure is that? What is it we would remember? Its sides are all equal, or its length, width and height, all three are equal. Okay, so here is a cube and one side is labeled as 2 centimeters. And we need to calculate the volume of this cube. So what do? 2 times 2 times 2, what happens to the unit? Okay, so let's try to write down our volume. So you will say 2 centimeter multiplied by 2 centimeter multiplied by 2 centimeter. So of course 2 times 2 times 2 is 8, and the unit will become centimeter cubed. That is how the volume has centimeter cubed as the unit, because it's 3-dimensional, so the unit also will get cubed. Okay, and when we talk about volume, you hear the phrase cubic feet or cubic meters, right? So volumes are always expressed in cubed, whatever unit you are using, and very often we will use centimeter cubed, which is also the same as milliliters. So in other words, we can write 8 centimeter cube or 8 milliliters. It's exactly one and the same. So volume of the liquids are usually measured in units of milliliters. So the glassware we have in the lab, they are all labeled as milliliters. That is why you need to remember centimeter cube and milliliters are one and the same, because when you do problems, you may have to use centimeter cubed. Okay? Now, how many milliliters are in 1 liter? 1000, right? Again, remember milli stands for thousandth. So 1 liter is 1000 milliliters. Now again, here are some containers which are 250 ml, 500 ml and 1 liter. So okay, so this is a 500 ml volumetric flask, this is 250, and this is, as I said, a 1 liter graduated cylinder. So let's do some conversions with volumes also. So the first one, convert 25 milliliters to liters. Again, follow the dimensional analysis pathway which I was showing you in last class. So the conversion we need to remember is between milliliters and liters. What did we just say? 1 liter is 1000 milliliters. So here is your conversion. Now how do we set up the problem? What are we given? What unit are we given in the problem? Milliliters. So we are starting with this quantity, 25 milliliters multiplied by, so we have to use this in a fraction form. Which goes on the top, which goes on the bottom? Milliliters goes on the top and the liters will be, oh wait a second, the opposite way. We are given milliliters. So whatever we are given, that should go on the bottom. So that means 1000 milliliters goes on the bottom, and we are looking for liters, so 1 liter goes on the tops. Therefore, the milliliters and milliliters get cancelled and you have your answer in liters. So how many liters is this? 0.025 liters. That is correct. Yes.
Can you just move the decimal point?
You can move the decimal point in this particular problem. When it is just straight away conversions like milli to liter or milligrams to kilograms, things like that, you can move the decimal point. But look at the second problem. Can you just move the decimal point and do the problem as it is? I mean, that is if you are not done the first step. Let's say this is the only problem you are given. Convert 25 milliliters to quarts, and this is the conversion given to you. Can you do it just by moving the decimal point? You will not be. That is why you need to know how do we convert. That is why I am showing you every single conversion in that specific form so that you will get used to that. So once again, let us start. So we have to convert milliliters to quarts. Okay? So we need a relationship between milliliters to quarts. Do we have a relationship between milliliters to quarts given? No. What we are given is liters to quarts, right? So what do we need to do? We somehow have to convert this milliliters to liters first. So if you can convert this milliliters to liters, then you can use this conversion. So the first step would be converting the milliliters to liters. Actually, you have done that in the previous step. It's exactly the same, right? So first step is converting this 25 milliliters to liters. You have done that. So here we can start with the 0.025 liters because we already did that. Now let's use this conversion factor. How do we set this up? What are we given? What are we looking for? So now what we have is liters. So from the conversion, liter part should go down. So 1 liter will be in the bottom, and we are looking for quarts, so that should go up. 1.057 quart on the top. So now the liters and liters can be cancelled, and how many quarts you have? 0.025 multiplied by 1.057. What do we get? 0.026 quarts. So that should be your answer. So if you learn this way, then you don't have to worry about even making a mistake of which way I move the decimal point, how many places I move the decimal point. No confusion whatsoever. Start with what the quantity you are given and use the conversion factor looking at the units. What you are given goes on the bottom. What you are looking for goes on the numerator. Okay, we will again, more detail, we will see those steps again. So yes, here is our answer. They have 0.0264 liters. Probably, let me see. Yes, we haven't learned the significant figures yet. You have to put your answer with 3 significant figures, and this has only 2. That's why they are given with 0.0264. We will learn the significant figures and you will understand that then. Your question? It should be quarts. This is a mistake. This publisher especially, this PowerPoint, this is the 3rd year I'm still correcting. They have a lot of printing mistakes, okay? So if you see something, please do let me know. We will correct it immediately. They do have a lot of printing mistakes in the PowerPoints. I've noticed that. So the answer is in quarts because that's what you are converting to. Questions so far? Where? Which step?
I can understand the 0.025 liters.
Mm-hmm.
And 1 liter on the bottom.
Yeah.
1.057 quarts.
Yeah.
And then I put it in the calculator.
Why? It's only one step. 0.025 multiplied by 1.057. It's just one single step. Have you pressed the multiplication sign on the calculator? If you have pressed some other sign, you might get some other answer. Double check. If you multiply those two numbers, you should get 0.0264. Okay, double check. So we talked about, you had a question? Let's just leave it right now. Don't worry about the significant figures. Yes, technically you need 3 there. But we will learn the rules if any of you are not familiar with the significant figures rules. So once you learn the rules, you will understand why some answers are given in with specific digits. Okay? So after that, we will follow the significant figures. Until then, I'm just going to be easy. Whatever you get, whatever you write, that's good. At least you have done the steps correctly, and if you have the number correct. So the next unit we are going to, our next physical quantity we are going to look at is density. So we talked about mass and volume, and density is the ratio of mass to its volume. And units are grams per ml in solids and liquids, or grams per liters in gases. Okay, so how do we get the units grams per ml for density? So we said density is the ratio of mass to its volume, or we have seen this from school. D is m by v, mass divided by volume, right? If you have an object's mass and its volume, to calculate the density, all you need to do is mass divided by its volume. Now let's write out the units also. What is the unit mass? Grams. For volume we have milliliters. So you have the density's unit, which is grams per milliliter. Or we can also have grams per, well, that is for gases. I'm just looking at an equivalent expression for this. Centimeter cube. You will see this also very often. Grams per ml or grams per centimeter cubed. Both are one and the same because ml is exactly the same as centimeter cube. For gases, it's usually grams per liter because gases occupy such a large volume. If you take the amount of a gas in milliliters, it would be very small. So to make the quantity, really a number which we can work with, we usually take grams per liters in terms of gases. So see table 1.6 for a listing of densities of some common substances. So this table is from your book. Here are some things which are given, and their physical states and density. So you can look at the helium, oxygen, both are gases. Here the density is given in grams per ml unit. So you can see how small the numbers are, right? So it will be difficult if you take the density of a gas with grams per ml unit. That's why for gases we usually use grams per liters. Our cooking oil is a liquid, 0.92. Water, which is perfect 1. And then mercury, which is a heavy liquid, 13.6. Gold, solid, 19.3. And then we have copper, zinc, other 2 metals. And then we have ice at 0.92. And it says at room temperature and normal atmospheric pressure except at 0 degree, except gases at 0 degrees Celsius and water at 4 degrees Celsius. Okay. So when we measure density can slightly change with the temperature or the atmospheric conditions, the pressure and temperature, because with the pressure and temperature, gases can change the volume. Okay. That's why we have to specify in terms of gases at what temperature and what pressure you are expressing the density, because it will change based on those two quantities. So again, as I said, density is mass divided by volume, and that is how we get the units. Now let's see that cube again. We had seen this cube with that 2 centimeter one side. What is the mass of this cube? If its mass is 11, well, if the mass is 11.2 grams, what is the density of this cube? So we have already calculated the volume of this cube, right? What was the volume? 8 centimeter cube. So we just have to plug in the numbers. Density is mass divided by volume, and mass is given 11.2 grams. Volume we had calculated 8 centimeter cube. So you will get an answer in grams per centimeter cube with the correct units. So what do you get? 1.4 grams per centimeter cubed. Yes, that's your answer. So calculating density, if you know mass and volume, it's just mass by volume. Now having said that, looking at this equation, if we know any of the two quantities, you can rearrange the equation to find the third quantity, right? If I'm given you mass and density, you can calculate the volume. Or similarly, if I'm given density and volume, you can calculate the mass. Okay, so we can rearrange the equation to calculate the third quantity. Now, which liquid is the most dense, which is the least dense? So here is a graduated cylinder, and there are 1, 2, 3, 4, 5, 6 different liquids in there with 6 different densities. Okay, with each color you can see there are 6 different liquids. What do you think? Which one has the most density? Which one has the least density? Looking at this, we can say that the volume of each liquid, they are all the same, right? Because the thickness of the layer of you see, it's the same. So when we calculate the density, the volume doesn't do anything now because volume of all the liquids are the same. So it is directly related to the mass of the liquid. And we know the heavier things will usually sink or go down, right? So the bottom one has higher density and the least dense liquid is on the top. Okay, now here is a picture. The author, Jim Burke, he is in Dead Sea. Dead Sea is the only place where you try to, drown yourself. You cannot do that. You keep coming back to the top. Why is that? What do you think by looking at this picture?
Salt is heavier than us, and it causes us to float up higher because we're less dense than the salt.
Well, does it happen in a normal ocean if you just go and, if you don't know how to float, you can float by, practicing. If you don't know how to float, you just jump into a pond or just regular ocean, would you be floating by yourself? No, you would usually go down, right? Because your body is denser than the water. But in Dead Sea, your body is less dense than the water of that Dead Sea. Well, the name Dead Sea comes because nothing can live in that sea. No fish, no other organisms can live in that sea. Because that water has a very high amount of salts and minerals dissolved in it. Very high amount compared to the regular ocean water you find all around the world. This water has a very high amount of salt dissolved in it, so the water is so thick. The water is so thick, it's thicker than the body or the denser than the body, so you will float in that sea. You don't need any special practice or any floating devices for floating. You will just try to be in that water and you will float. So here is two equal volume metals. As you can see from the size of the cube, one is gold, the first one Au, the other one is aluminum, Al, and you can see that their volumes are the same. And it says gold has a greater mass than that aluminum. Okay, which one will have the greater density? Gold. What is your reasoning? Explain that to me. So once again, we said density is mass by volume, right? So both of them have the same volume. So if you calculate the density of each, this number is exactly the same. So that doesn't do anything to the calculation. So basically this density is going to be proportional to whatever mass it has. So if gold has greater mass, then it has greater density. Aluminum has less mass, therefore it has less density. Now, if we take a can each, regular soda and diet soda, and if we put that in water, we can see that the diet soda will float, whereas the regular soda will kind of go to the bottom. So looking at this, now we can say which one is more denser, which one is less denser. The regular one is more dense. The diet one is less dense. Well, if you look at the cans and read the volume, they are exactly the same. So where does this density difference comes from? It has to come from the mass. Why there is a mass difference? Do we know? No, there is something which is specifically responsible for it. What is different in the regular soda and diet soda? The sugar content. Regular soda is sweetened with sugar, whereas diet soda is sweetened with artificial sweeteners like Splenda, aspartame, all that stuff. If you take sugar and Splenda, well, you know this. Splenda, you take a packet, such a small amount, and it says that small amount is equal to like 1 tablespoon of sugar, right? So if you take 1 tablespoon of sugar and the amount of Splenda that needs to sweeten just like 1 tablespoon of sugar, which one has greater mass? The regular sugar. The sugar is really heavy compared to the amount of Splenda you need. So if you take, to attain the same sweetness, 1 by sugar and 1 by Splenda, you will have very small amount of Splenda, whereas you need a lot of sugar to make the same sweetness. And all that sugar dissolved in that soda, it adds up to the mass. And that is why your regular soda is heavier than the diet soda, just the sugar content. Now, we all know that when we put ice cubes in water, in a glass of water, ice will float onto the top. So now we know that is because ice has less density than water, right? If ice was more dense than water, it should go to the bottom. It doesn't happen. Ice would always come to the top. So ice has less density than water. Why is that? Both are made of H2O molecules. So what happens? If it's not separating, if you look into the structure of ice, when water freezes, it freezes in a specific hexagonal pattern, and that leaves a lot of space in between. So as you can see, like this is just liquid water, and when it freezes, this arrange in a specific like 6 water molecules in a kind of a circle with a lot of space in between. And this shape keeps continuing. Okay? So you can imagine there is a lot of this empty space in between. So empty space in between means less material in it, less water molecules in there, right? For the same volume. So ice is less denser than water because less mass of water molecules. Volume could be the same, as you can see. It's the same volume, same circle. But the amount of material, the mass of the water molecule, if you take in both circles, ice has less mass, therefore lesser density. Okay, let's have a clicker question. Do we all have the clickers? What?
Yes.
That's fine. When you use it today, it will get registered. Okay? If you have already done the registration on the website, this is the last step. You have this one more week, that is today and Thursday, to buy and finish your registration and all that. Okay? From next Tuesday onwards, whatever clicker quizzes we do in class will count towards your grade. All right, are we ready for the question? Everyone's clicker is out. Here is the clicker question. So, carbon dioxide bubbles in Anna's soda rose to the top. In soda, when we open the bubbles we see, that is dissolved carbon dioxide. So the question is, how does the density of the carbon dioxide compare to the density of the liquid that makes up Anna's soda? So think about what we just talked about density, what goes to the top, what in the bottom, and then choose one answer and choose the correct answer, okay? You don't need much time, I'm going to give you still a minute. Do you all have clickers today? You don't have, okay. So rest all 18 has clickers? Okay, so 17. I need to see one more answer then. I'll stop at 1 o'clock. Not 1 o'clock, I'm sorry. At 1 minute, okay? Oh, there it is, all 18. So no need to wait. All right. What's the answer? The liquid in NA soda is more dense than CO2. So the bubbles rose to the top means the bubbles are less dense. Right? So the liquid has to be more dense. Good. Now let's see what we did. I think that's what gives our answer. Okay, most of you got it right, but there are 2 wrong answers. What happened? The liquid in NA soda is less dense than CO2. If the liquid was less dense, then the bubbles should be on the bottom and the liquid should be on the top. Is that what the question says? It says the bubbles are on the top, the liquid is on the bottom, right? So now how do I make it correct answer? Yes, that is how you do in the new one. Good. This is a new version of clicker, guys. The other one, at the when I move it around, I get the option and just click, and that used to get green. Okay.
So how do you know if you got our name with it?
How do I know your?
I registered on the website and I just clicked it and it went green and you got my vote, but then do you know like?
I have a grade book with all your names on it. Otherwise, how would I see what each person answered, right? Because if it is counting towards your grade, I need to know who answered it right and who answered it wrong. All right. Now let's talk about temperature. So we talked about mass, volume and density. So the next unit we will use very often is temperature. So temperature is a measure of how hot or how cold something relative to a standard. Okay? Now usually we measure temperature with a thermometer. We all know that. And temperature is independent of the sample size. That means it doesn't matter if you have 1 glass of ice water or 1 gallon of ice water. You can take the temperature of that water. It doesn't say you need at least a glass to measure the temperature. No. It could be any amount you have. You can measure the temperature. And the units we use in temperature measurements, degrees Celsius and Kelvins, not Fahrenheit units. Okay? The unit which we usually talk about, in weather as or usually at home, it's Fahrenheit, but we don't use that in scientific calculations. The SI unit for temperature is Kelvin, K, or the other one is degrees Celsius. I think we will be using most often the degrees Celsius unit. Here is the relationship between Kelvin and degrees Celsius. Temperature in Kelvin is whatever temperature in degrees Celsius plus 273.15. And here is a conversion or an equation to convert between Fahrenheit and degrees Celsius. A temperature given in Fahrenheit, if a temperature given in degrees Celsius, if you want to convert that to Fahrenheit, multiply that temperature by 1.8 and then add 32. Here is a picture which gives you all 3 scales and the relationships. This should make it clear to you. So the first one, this is what we are all familiar with, right? The Fahrenheit temperature. We know that ice will melt at 32 degree F or water will freeze at 32 degree F, and the room temperature is usually 77, even though we don't keep the room at 77, or in scientific calculations, something when an experiment done at room temperature means this is the temperature you mean, and the liquid water boils at 212 degree F. We know that. And the lowest possible temperature in the F scale is negative 460 degree F. That is the lowest possible temperature. Now, here are the two scales, the right side. Those are the two scales usually you will see on scientific calculations. The middle one is the most oftenly used one. The degree Celsius scale is based on the properties of water. So 0 degrees Celsius is where the water will freeze, we know that, and 100 degrees Celsius is where the water will boil. And the room temperature is 25 degrees Celsius. And the lowest possible temperature in degrees Celsius is negative 273.15. Now if you look at Kelvin, you will see how these two relationships will come in picture. Kelvin, the lowest possible temperature, 0 Kelvin, which is called the absolute zero. Okay? And in the water will freeze at 273.15. So if you look at the freezing points of degrees Celsius and Kelvin, why is it not? Okay, right here. And Kelvin, you can see one is 0, one is 273.15. So a temperature given in degrees Celsius, just add 273.15 to it, you will get the temperature in Kelvin. Or a temperature given in Kelvin, subtract 273.15, you get the temperature in degrees Celsius. So that is the magic number you have to remember, 273.15. Now that 0.15, forget about that. Just for our calculation purposes, it's good enough if you just use the 273. Okay? So anything in degrees Celsius, add 273 to it, you get Kelvin. Anything in Kelvin, subtract 273 from it, you get degrees Celsius. Don't worry about the Fahrenheit. We will not be using that in calculations at all. You will not have thermometers which measure in Fahrenheit. Okay? So I'm not going to focus on that at all. So it's going to be degrees Celsius or Kelvin. Now the last thing in chapter 1, we will all look at scientific notation or exponential notation. How do we use that in calculations? Then we will look at the rules of significant figures. And then one more, units and conversions. We will do it one more time. So scientific notation, when we work with very large numbers or very small numbers, you use scientific notation because it's difficult to work with very large or very small numbers. You need to remember the rules for addition, subtraction. Well, I don't think addition, subtraction they are teaching you here. No. Mostly you will be doing multiplication, division, or raising something to a power. Those are the three operations you are going to do using scientific notation in chemistry calculations. So we are going to focus only on that. The three operations are most common are multiplication, division, and raising the power. Now in multiplication, what do you do? When you multiply two numbers with scientific notation, you would just multiply the coefficients and add the exponents. So here are two numbers, 4 into 10 to the power 6. So this 4 is called the number part, the coefficient. And this 10 to the power 6, this is called the exponent part, right? So in scientific notation, a number has two parts, the number part and the exponent part. So when you do multiplication, you will multiply the numbers, that is 4 and 1.5 are the numbers. So you multiply that, you will get 6. But what happens to the exponents? Are we multiplying 6 and negative 3? No, we are not. We are adding the exponents. So this is the rule here. When multiplying numbers in scientific notation, multiply the coefficients and add the exponents. Okay? So you multiplied the numbers, you get 6, and the exponents are 6 and negative 3. So you have to add those two, 6 and negative 3. So you have to remember the rules. When you add a negative and positive number, what happens? You subtract or take the difference and you will have the larger number sign in your answer. So the larger number is 6 there, therefore your 3 will have a positive sign, so 6 into 10 to the power 3. Now when we do division, what happens? Once again, you take, when you divide the numbers in scientific notation, divide the coefficients and subtract the exponents. So 4 and 2 are the coefficients in your two numbers. So you do 4 by 2, which is 2. But what do you do with the exponents? You are subtracting the exponents. Pay attention to the signs. So the first exponent is negative 2 and you are subtracting the second exponent, which is 3. So negative 2, negative 3 is negative 5. Okay? So don't just jump into, oh okay, 2 and 3, so 2 minus 3, negative 1. No, this is not just negative 2 and positive 3. Remember, you are subtracting the exponents, so you write it out. If you can't, if you are not very familiar with doing the numbers with signs over your head. So negative 2, negative 3 is negative 5. Now the third operation you would do is raising the exponent to a power. So you have already a number with an exponent and you have to raise the entire number to another power. What would you do? Raise the coefficient to the power and multiply the exponents. So 3 into 10 to the power 4. This is your number. You want to raise the entire number to a power of 2. So raise 3 to a power of 2. So 3 to the power 2 is 3 times 3, 9. But what do you do with the exponents? So this is 10 to the power 4. You are raising that to a power of 2. Here you are multiplying the exponents. So you will get 4 times 2, 8 as your new exponent. So these are the 3 rules when you work with numbers in scientific notation. Okay? If you are not remembering what numbers in scientific notation, please do read that math toolbox in your chapter 1 and pick up your old algebra book, okay, and revise what do you do with positive, negative numbers, addition, subtraction, rules to remember, scientific notation. Revise all those things if you haven't done algebra in recent past. Okay? So you need to be remembering all those things. So let's do an activity of all those 3 rules which we learned. So here our first case is multiplying two numbers. 6.78 into 10 to the power 3 multiplied by 5.55 into 10 to the power negative 4. What do we do? So the first question. So what do we do? The rule is multiply the coefficients. So when we multiply the coefficients, what do we get? 37.62 times 10 to the power. What do we do with the coefficients? 3 and negative 4. We are adding. So 3 negative 4 is 10 to the power negative 1. Okay, now can I leave this as my answer? What is wrong? No, negative power is good. Not significant digits, something else. Well, significant digits is 1, something which we have to focus on, but before that, yes. Yes, the 37.62. If you don't remember scientific notation, remember in scientific notation, the number part has to be between 1 and 9.9. It cannot be more than that. If it is not a number between 1 and 9.9, you have to move the decimal point to adjust it to that and do the necessary corrections at the exponents. So 37 is definitely above 9.9, right? So you have to move the decimal point to get a number between 1 and 9.9. What can you do to this number? How can you move the decimal point? Move one place to the left. If you move this one place to the left, now you get 3.762. Is that number between 1 and 9.9? Yes, we are good. So the number part is okay. What happens to the 10 to the power part? It was negative 1 before, but now we moved the decimal point to the left. What do you do? each decimal point we move, each place is 1. What do you do with that 1? When you move or left, move left or move right, what do you do? Add 1 or subtract 1? That is the question. When you are moving to the left, you are subtracting 1. Okay. So if you are subtracting 1, then what happens? So you had negative 1, you are subtracting 1 more there. So your power is now 10 to the power negative 2. This should be your correct answer, expressed correctly in scientific notation. Everyone go home today and revise your scientific notation from your Algebra 1, okay? Everyone is supposed to have Algebra 1 at least, or if you haven't taken that, you should have been tested out of Algebra. So you should know this by now. Please do pick up your Algebra book and revise it if you don't remember. Don't think that, oh, that's something which I don't worry about. Okay, second one, 2.99 into 10 to the power negative 9 divided by 4.03 into 10 to the power negative 6. In division, what do? You divide the numbers, but what do you do with the exponents? Subtract. Okay, let's divide the numbers. So when you divide 2.99 by 4.03, what do you get? 0.742. I'll stop there. 0.742 multiplied by, let's do the exponent part, 10 to the power negative 9 minus 6. Pay attention to this negative signs. Okay? This is the first exponent, negative 9. Subtract the second exponent, which is negative 6. So what happens here? Negative 9 minus 6 will become, this 2 minus signs will become a positive sign. So negative 9 positive 6 is, so we will get this part as 10 to the power negative 3. Okay. Now, so your number is 0.742 into 10 to the power negative 3. Is that expressed correctly in scientific notation? No. This is again less than 1. So what do? We have to move the decimal point one place to the right. So we will get 7.42 into, what happens to the exponent? When we are moving to the right, what are we doing? Add one place. So now negative 3 plus 1. Negative 2. Everyone is following, right? Okay. Now the last one. 7 into 10 to the power 3 raised to the power 4. What did we say when we raise something to the power? 7 raised to the power 4. What is that number? 7 times 7 times 7 times 7. Well, something raised to the power 4 means it's not 7 times 4. You know that, right? 7 times 4, 7 raised to the power 4 means 7 multiplied by 7 multiplied by 7 multiplied by 7. 70,000? Oh. 72,000? 2,401. Okay, let's write that as it is, into 10 to the power, what happens? What are we doing with the exponents? We are multiplying them. So 3 times 4, you get 10 to the power 12. Again, is that correctly expressed in scientific notation? No. Where is the decimal point in this number now? If a decimal point is not shown, then after the last digit. So the decimal point is right here. Oops. Okay, so the decimal point is right here in this number. Where do you have to move it in order to get a number between 1 and 9.9? Between 2 and 4. So you are moving this decimal point to here. 2.401. How many places did we move? 3 places. So what are we going to do? Subtract 3 from 12. So 12 minus 3 is Wait a second. Oh yes, that's right. 12 minus 3 is 9. I know. What, guys? We did the rules wrong. Completely wrong. Let me get a new, oops. Let me get a new screen and write down the rules, not just, how do I get a screen? I can get a black screen. Okay. So, scientific notation rules. We have to revise that.
So, none of those are correct.
Well, the only rule we went wrong is when we go left, are we subtracting or adding? When we go right, are we subtracting or adding? That's where went we wrong. So, instead of just, automatically following, let's just try to understand and make sense. So, let's say we have 3.2 and we want to move this decimal point, let's say we have 320, here is the decimal point, we want to move this here. We are moving left 2 places. Moving left 2 places mathematically means what? Not subtracting, dividing by 100, right? If you are moving 2 places to the left, that means you are dividing that number by 100. So let's say we had 10 to the power 2, no, not 2, 2 will become problematic. Let's say we had 10 to the power 3 here. This was our original number, 320 into 10 to the power 3. Okay? So we are moving 2 decimal point here. That means we have divided this number by 100. Remember, whatever you do, all these adjustments, mathematically the value should not change. So if you have done a division here by 100, to compensate that, you are going to do a multiplication here by 100. So that mathematically the number will not change. Now, multiplying by 100 means what? You can move 2 decimal points to the right. That is equivalent to multiplying by 100. So if you are moving 2 decimal point to the right or multiplying by 100 means if you multiply 10 to the power 3 also by 100. Okay, how can we write that? 100, remember 100 is 10 to the power 2.
So if you divide it, you move 2 to the left.
So here basically you are adding 2 places. That's where we went wrong.
But if you divide it, you go 2 to the left. And if you multiply, you go 2 to the right.
Yes, that is the general rule. If you are dividing by 100, you are moving 2 places to the left. If you are multiplying by 100, you are moving 2 places to the right. But here, I'm trying to explain why it has to be moving to the right. If you are moving decimal point to the left, why you have to add here. That's what I'm trying to explain. Does this make sense? So mathematically, the number is not changing now. Your new number is 3.20 into 10 to the power 5, which is the same as 320 into 10 to the power 3, your original number. So the first rule, when you move the decimal point to the left, we are adding 1 to the exponent, not subtracting. That is where we went wrong. So similarly, if you are moving the decimal point to the right, let's say you have 0.00320 into 10 to the power 3. This was your original number. We want to move the decimal point actually 3 places. Okay. So we are moving the decimal point 3 places to the right means we are multiplying here by 1000. Moving 3 decimal places is equivalent to moving 3 places to the right equivalent to multiplying by 1000. That means to take care of that, let me say my original was 10 to the power 4, okay? Not 10 to the power 3. So we have to divide here by 1000, or 1000 is 10 to the power 3, and what are we going to do with that? Subtract it. So you will do minus 3 on the side, so your new number will be 3.2 into 10 to the power. So what is our rules? Let's say that one more time to get it here. Let's not make the mistake. When we are moving the decimal point to the left, we are adding one place to the exponent. If we are moving the decimal point to the right, then we are subtracting a place from. Our multiplication thing was good. I mean, raising to the power. Well, there also we went wrong because we subtracted. We moved to the right, and what did we do? Well, didn't we do that right? No, we moved to the left, and right here. So we moved to the left, so we should have added 3 place. So we should have got 10 to the power 15 here. Let's correct all this. Here we moved to the left, so we should have added 1. So 10 to the power negative 1, positive 1 means 10 to the power 0. Here we have moved 1 place to the right, so we should have, here we moved 1 place to the right, so we should have subtracted 1, so we should have got 10 to the power negative 4. Now we are good. Did everyone make the corrections? So one more time. Moving decimal point to the left, we are adding. Moving decimal point to the right, we are subtracting. Yeah, even I needed a revision, huh? Yes.
Is it always going to be 10 to the power?
Yes, in scientific notation it's all based on 10, so it's always going to be 10 to the power. Okay, I'll go in the order.
10 to the power 1, can you simplify that in scientific notation and just leave it as 10?
Yes,
Okay.
10 to the power 1 is exactly the same as 10.
Yeah.
Those are supposed to be the right answers. It says 10 to the negative 2. We have 10 to the negative 4, number 2.
That this is wrong then. Yes, they did the same mistake we did in the beginning. So this has to be what? Negative 4, that's what we got with the correct rules. Didn't we correct it? This was what we got, but then let's do that.
Yeah,
but
it
we
says
didn't get
1.20. We got
1.20.
7.42, so I think half power on
Oh, are we having a problem here?
that. It looks like it.
What is it? What did we get?
We got 7.48.
Okay, so apparently, what did they do then here? 2.99 divided by 4.03, there is no way you can get 1.2 or even 0.1.
Switch it.
I really don't know how they got this number. This is wrong. Whatever we got, that's right. Because if you punch in the numbers in the calculator, do you get anything near 1.2?
Only if you switch it.
Switch it. That is, maybe they did 4.03 divided by 2.99. Okay, they switched the order. That's why. All right, that is wrong. What is our answer? Let's write that down. 7.42 into 10 to the power negative 4. Okay, and this one we finished. 2 into 10 to the power 15. Someone else also had a question somewhere there. Was that the same question? Why the number is wrong? Okay. Okay, now the last thing, we are going to learn the significant figures, but before that we need to understand the meaning of these two terms, precision versus accuracy. What do we mean by precision? Precision of a measured number is the extent of agreement between repeated measurements and its value. Or let's say you are trying to measure the temperature of let's say 5 glasses of water, okay, and all water comes from the same tap. So if all your measurements are, all those 5 measurements are very close to each other, we will say your measurements are precise. If all 5, if they agree within each other, if they are close together, we will say they are precise. Now, in order to be the number to be accurate, what do we mean by accuracy? Accuracy is the difference between the value of a measured number and its true value or its accepted value. Now, I'm going to say, okay, the temperature of the water is 25 degrees Celsius. So that is the true value, okay, or the accepted value. Now you are going to see what are the numbers you got. Let's say if you had like 5 different numbers, 24.9, 25.1, 24.7. So you are going to see how close your value is to the true value. If they are close, then we can say, yeah, your number is good. It's accurate. 24.9 and 25, there is only 0.1 difference, right? You are good. But let's say you are coming up with 22, then I would say, oh, that's a little bit far away from the true value. So your number is not accurate. So accuracy means how close your numbers or how close your measured numbers are to the true value or the accepted value. Precision means how close your measurements are within each other. So again, if you have all 24.9, 25.1, 24.7, they are all kind of close together. But if you have 16, 18, 22, 24, 28, are they agreeing each other? They all came from the same tap at the same time. So you don't have any precision. Okay? Now this picture, this would illustrate exactly what do we mean by this. So what is this game called? Horseshoe. So your target or your true value is this. Okay? Let's stick in the middle where you are going to put all your horseshoes in. Now this person, as you can see, all of them are in there, closer to the, as close as possible to the true value, and all of them are within themselves also, they are all close together, right? So we can say he has good accuracy and good precision. Here, all his horseshoes are very close to each other. He has good precision, but he doesn't have any accuracy or very poor accuracy because this is the true value. Is he close to the true value at all? No, he is far away, but all his measurements are within themselves. They all very close together. They all agree each other. So he has good precision. Now the last picture, he doesn't have accuracy. He doesn't have precision because all the horseshoes are just scattered. None of them are close together. None of them are agreeing within themselves, or they are not close to the true value. So he doesn't have accuracy or precision. Now you are clear what do we mean by accuracy and precision? Okay. Now, when we do mathematical calculations, we need to follow some rules, otherwise probably we will overstate the accuracy. Okay? When you do a calculation, if you get 5 digits on your calculation and if you start using those 5 digits in every single step, towards the end you will end up with such a number with so many digits, you are kind of overstating the accuracy. Or 25 of you will come up with 25 different answers. So we need some rules to follow. What do you do? How do you round off numbers when you do calculations? So the significant figures will give us those guidelines. So there are 4 different rules to learn. The first rule is all non-zero digits are significant. So say for example the number 9.876. How many significant figures are there in that number? 1, 2, 3, 4. All non-zero digits. Easy, right? The second one, zeros to the left of the leftmost non-zero digit, often called leading zeros, are not significant. So let's look at this number, 0.009876. How many significant digits we have here? These 2 zeros, we don't count them. Okay? Or even this 0, we don't count these because those are left of the leftmost non-zero digit. So here is the leftmost non-zero digit, 9. So any zeros before that we don't count as significant figures. So 1, 2, 3, 4. Again, we have only 4 significant figures in that number. First thing you have to remember is significant figures are not the same as the decimal places. Okay? If anyone is thinking that, please take that out of your mind. Significant figures are not the same as decimal places. The third rule is zeros at the right of the rightmost non-zero digit, typically called trailing zeros, are significant. So here is our number again, 9876.000. Okay? Now let's read the note also before we understand this. A decimal point is mandatory for rule number 3 to be true. Otherwise, the number of significant figures is ambiguous. So here we have a decimal point, and the rule says zeros to the right of the rightmost non-zero digit are significant. So the rightmost non-zero digit is 6. Zeros to the right of that, these 3 zeros are right of this 6, and we have a decimal point in the number. Therefore, this will count. We cannot neglect them. So having said that, there are 1, 2, 3, 4, 5, 6, 7 significant figures in that number. Now, what if you did not have a decimal point given, like the number was just written like this? Then it is, even though we assume when we don't see a decimal point, the decimal point has to be here. If it is not given, and if you are counting the significant figures, it's kind of, a bit gray area. You can say, some people might come up with, well, there is no decimal point given, so I will not count this 0, so there is only 1, 2, 3, 4. Or some people would say, well, when there is no decimal point given, you should assume the decimal point is at the end, so here is the decimal point. Therefore, 1, 2, 3, 4, 5. So there is a confusion, 4 or 5, right? That is why a decimal point is mandatory for this rule number 3. If there is no decimal point, it becomes a bit gray. If you say 4 or 5, technically both has to get credit or both has to be right. Okay? But if there is a decimal point, then we have a specific answer. So the zeros to the right of the rightmost non-zero digit will count. Now the last rule is zeros between 2 non-zero digits are significant. So here is the number again, 9.800076. So these 3 zeros, those are between 2 non-zero digits, between 8 and 7, 2 non-zero digits. So they are significant. So the total number of significant figures in this number is 1, 2, 3, 4, 5, 6, 7. 7 significant figures. So this is how you will count the significant figures in a number. So once again, all non-zero digits are significant. Zeros to the left of the first non-zero digit are not significant. Zeros to the right of the rightmost non-zero digits are significant if there is a decimal point. Zeros between 2 non-zero digits are significant. Now, how do we use them in calculations? Okay, first let us practice this. What is the number of significant figures in these given numbers? 26. 2. 2 non-zero digits, so they both are going to count. Second number, 19628.00. Would we count these 2 zeros? We will, because there is a decimal point. So it has to be, let me see if it is giving answer one by one. Oh, not all. So the second one has to be? Second one is 7. Now this one? Only 4. Do we count these zeros? No, we don't. They are left of the leftmost non-zero digit. So we will not count. Yes?
But with a decimal point there, you would count those zeros?
No. If this 0 was, let's say, 1, then we will count these 2 zeros. Since this is a 0, we will not count it. That is why I said Do not think that decimal points and significant figures are one and the same. They are not.
So how would you write that number?
This number has only 1, 2, 3, 4, 4 significant figures. Oh, you are talking why it has a decimal point? That will come only, the zeros are to the right side. If you have a decimal point, you will count them. But when the zeros are on the left side, you will not. How about this number? Something in scientific notation. We will count the significant figures only for the number part. This exponents doesn't come into the exponents doesn't come into the significant figure rules. Okay? So 10 to the power 19 is the exponent part. You don't worry about that. You will look only at the number part. 9. So it's a non-zero digit and just 1. How about this one? Another scientific notation number. There is a decimal point. There's 0 in between. Do we count the 0? Yes. We will. So 1, 2, 3, 4, 5, 6, 7, 8. Do we have to worry about this part? No. So yes, there is our answers, 2, 7, 4, 1 and 8. Okay, so everyone now can count the significant figures in a given number, right? Now, what do we do with it? When you perform calculations, your final answer must reflect the number of significant figures in the least accurate or most uncertain measurements. Now, this is different for multiplication and division and addition and subtraction. In multiplication and division, your answer should have the same number of significant figures as the least accurate measurement, or the numbers you are using in your multiplication and division. If you follow through this example, the first number has 1, 2, 3, 4, 5, 6 significant figures. The second number has 1, 2, 3, 4, 5 significant figures. The third number has how many? 2. Your answer should have only how many?
2.
Only 2 significant figures, because among the numbers you have used, this is the one with least number of significant figures. So your answer also should have only 2. So when you multiply all this, if you get a big number, you have to correct it according to the significant digits rule. So you should have only 2. How can you do it? With the help of scientific notation. Okay? So your answer should be expressed as 1.3, which is only 2 significant digits, into 10 to the power 5. Yes?
I did the homework.
Mm-hmm.
And one of the problems, I went and checked the answer in the back of the book to make sure I was right, and it was giving me, like, for example, the first one was 1.2 times 1.216, and in the back of the book it said there was 1.5 significant numbers. I don't understand why.
1.5 significant numbers?
I didn't see
Yeah, significant figures cannot be fractional numbers.
It was, I started the homework with the wrong homework too, because
Okay.
throughout the chapter, there's like 1 point something too. So
Okay.
back to the answers, it's like that too.
Well, my homework problems are the end of the chapter exercises, not in between the chapter, okay? So make sure you are doing the right question and checking the right answer from the book.
I know I was doing the right questions, they just wrong.
1.5 is your answer, not the number of significant figures. So those are 2 different things, right? Answer is one thing. Now, how we should express our answer, using how many significant figures? That's what we are trying to figure out now. Okay? Okay, so that is the rule for multiplication and division. That is, whatever number you use, the number with the least number of significant digits, that many significant digits should be in your answer also. Okay? So here, since we had 6, 5 and 2, your answer should have only 2, because one number has only 2. But in addition and subtraction, the rule is different. When you add or subtract, you are going to pay attention only to the places after the decimal point. So the rule is, again, your final answer must reflect the number of significant figures in the least accurate measurement. So what do? Once again, here are three numbers. We have 234.506, then 0.12, then we have 4455.9. If you are adding all this is the answer we will get, right? We will bring down 6, 2 plus 0 is 2, 9 plus 1, 10, 5, 15. So you will carry forward 1 to the next step. You know the long addition. You did the addition. Now what do? We will pay attention to each of these numbers. How many places are there after the decimal point? The first number has 3 places after the decimal point. The second number has 2 places after the decimal point. The third number has only 1 place after the decimal point, right? So your answer should have only 1 place after the decimal point. The least number of decimal places among the 3. 1. So your answer also should have only 1. So typically you will just say goodbye to that 26. You will express your answer as 4690.5. Now when you round off or when you say goodbye, what if instead of the 2, let's say if this number was a 76, then how would you round it off? This will be rounded off as 0.6. Remember that if a number is 5 or above, when you eliminate that place, you will add 1 to the previous number. If a number is from 0 to 4, then you will just neglect it. You won't change anything. Okay? So these are the rules for using significant figures in calculations, and I think we will save the dimensional analysis, which is the last thing, for next class because I need to take your attendance.